So this lecture is going to go over the effect of temperature on our spontaneity of a reaction. And so to start off, we'll look at a model reaction. And the model we're going to look at is just the boiling of water, the conversion of liquid water into water in the gaseous form. And so when we think about this reaction, we can also recall that when we think about the reaction, the delta S net, the total change of entropy, is equal to delta S of the surroundings plus the change in entropy of our system. And so when we think about this, and we think about what's going on here, we can first say, let's think about the system for a second. And when we think about the system, what is the entropy change of the system? Well, we're going from a liquid to a gas. And as we do that, the molecules are going to gain molecular arrangements. There's more places for those molecules to be. And so because of that, anytime you go from a liquid to a gas, our system, this delta S of the system is going to have a positive change in entropy. It's going to be greater than 0. All right. We can also look at this and say, all right, well, what about this change in entropy of the surroundings? So what's going on here? And before we get to that, let's consider two situations. Let's consider the case where this reaction is performed at 95 degrees Celsius. And then we'll consider the case where this reaction is performed at 110 degrees Celsius. And as we do this, recall that the boiling point for water is 100 degrees Celsius. So when we think about this, in these two cases, at 95 degrees in this first case, we might know that this is below the boiling point. So therefore, delta S net, right, this is a non-spontaneous reaction. So delta S net must be less than 0. And in the second case, if we're at 110 degrees, this is above the boiling point. So if we're above the boiling point, then we predict water will boil, go from a liquid to a gas spontaneously. So in this case, delta S net must be greater than 0. All right, and we know that again because in the first case, this must be a non-spontaneous event. In the second case, this is going to be a spontaneous event. Now, if we come back to our equation over here, right, we said delta S net is equal to the change in entropy of the surroundings plus the change in entropy of the system. So let's think about this term of the surroundings now. So if we think about that surroundings, what's actually taking place? Well, if we think about what's happening in the surroundings as we go from a water in the liquid form to water in a gas, what has to happen is we have to break our IMFs, right? In order for that water to go from a liquid to a gas, we have to put in energy, we have to break the intermolecular forces of attraction to separate those water molecules. And so that is going to take energy. And in fact, it's going to require heat energy. So the surroundings have to lose energy, right? They're giving up energy to the system. They're giving the energy so the water can break those IMFs and turn into a gas. And so for that reason, when we think about this, the delta S of the surroundings is going to be less than 0. It's going to be a negative value because it's giving up this heat energy. It's losing energy, losing arrangements of energy. And so the entropy is going to be less than 0. So that means when we think about our equation up here, our delta S net, this delta S of the surroundings is a negative term, and delta S of our system is a positive term, right, for this particular change, which means that there must be a temperature dependency. And that's what we're seeing here, right? We said at 95 degrees, this is a non-spontaneous reaction. At 110 degrees, this is a spontaneous reaction. And all we're really saying is which one of these two terms wins out. If the change of the delta S of the system is bigger than the change of the delta S of the surroundings, it's spontaneous. And if the reverse is true, if the delta S of the surroundings is bigger than the delta S of the system, right, then it has to be a non-spontaneous reaction. So we can even write that in up here and say, in this first case at 95 degrees, we know that the delta S of the surroundings, oops, let me make that a little cleaner there. Delta S of the surroundings has to be bigger than delta S of the system. And in the second case, the delta S of the surroundings is less than the delta S of the system, right? Now, the other key, what we said, is delta S of the surroundings was related to the heat energy and it's related to temperature. And with those two things, we can actually come up with another equation and say the delta S of the surroundings, right? When we think about what this actually is, we can think about delta S of the surroundings as being related to delta H, our enthalpy term, divided by our temperature. So there's our temperature dependency. Now, the last distinction I'm going to make is the delta H we're going to talk about is the delta H of the system, right? Because we're talking about breaking the bonds, the intermolecular forces of attraction in the water molecules. And because in this case, we're talking about energy of surroundings, and in this case, we're talking about energy of the system, right? Recall that the system and the surroundings always have to have opposite energy flow. We're going to put a negative sign in front. And that negative sign right here is key. That's just saying we have the reverse energy flow from system to surroundings. So it leaves the surroundings, it goes into the system, or vice versa. But this equation that we just derived, right, this is our relationship between the system and our surroundings in terms of this, the entropy of surroundings and the entropy of the system.